In this episode, we discuss OPC UA and time-sensitive networking for real-time field-level communications over Ethernet, sensor-to-cloud communication, and the role played by the combination of these technologies in Industry 4.0. My guest on this episode is Bhagath Karunakaran. Bhagath is the CEO and founder of Kalycito, an industrial IoT software solutions company with full-stack edge-to-cloud capabilities. Kalycito is a recognized thought leader in this space due to its pioneering effort to create an open-source ecosystem around OPC UA and time-sensitive networking on real-time Linux. In 2018, Fraunhofer IOSP, Kalycito, and the Open Source Automation Development Lab formed a working group to create a publicly available framework for real-time communication over Ethernet based on OPC UA and TSN. This included works such as the world's first OPC UA PubSub implementation and the recently launched Phase 3 of the project, which has received support from companies such as ABB, ARM, B&R, Intel, Contron Europe, and Siemens. A quick thank you to our sponsors. This episode is made possible by our friends at HiveMQ, who are providers of an enterprise-grade edge and cloud-based MQTT broker. I use it for my own IoT applications, and they have a free cloud version which allows you to connect up to 100 IoT devices. So please do check it out to help support this channel. Welcome to the 4th generation podcast here on Industry 4.0.tv, which is a series of weekly interviews designed to help you learn industrial IoT from some of the world's leading practitioners. So if you're new here, please make sure to subscribe and click on the notification bell to make sure that you never miss any of the videos. If you find this conversation interesting, please review it with 5 stars on Apple Podcasts, follow on Spotify, and you can also connect with me on LinkedIn at Kudzai Manditereza. Now, here's my conversation with Bhagath. Okay, Bhagath, I would like to welcome you to the 4th generation podcast here on Industry 4.0.tv to discuss OPC UA over time-sensitive networks, which we'll refer to as TSN throughout this talk. So welcome.
Yeah, hi, Kudzai. Nice to meet you.
Okay, so a lot of people in the audience here, I'm sure, are already familiar with OPC UA. So maybe to set the stage here, you could begin by defining what time-sensitive networking is and how it works.
Yeah, sure. So if you look at time-sensitive networking, that is the name of a task group within the IEEE that's tasked to do real-time networking with the Ethernet. I mean, to extend the existing Ethernet standards to do time-deterministic communication. Now, let's try to understand what this is and why this is important. Traditionally, Ethernet, when it was invented, it had a particular feature called CSMA-CD. That's carrier sense, multiple access with collision detection. So these were networks that were built using coaxial cables, where you then tap the cable to connect your computer systems. And the technology was built in a way where multiple computers can talk simultaneously. And if there is a crosstalk, some of the computers can back off and wait for their turn to communicate. So this was excellent when it comes to office network. You know, when you want to print something, 2 computers trying to do that, and then one backs off for a random time, one guy gets to do the work and then comes back. So this was excellent when it comes to the office network. And that's primarily the reason why Ethernet became so successful. On the other hand, when you try to use Ethernet in some other industries, for example, in professional audio video broadcasting, where you had to have the lip syncing and the lip syncing of the video and the audio, or when you talk about communication within a car environment where some of the communication cannot delay a lot, or when it comes to 2 robots talking to each other, Ethernet was not that great. You know, this carrier sense multiple access where you have a random back off will not help you guarantee time. In fact, this random back off was, the second time if there is a crosstalk, it was an even bigger number and a bigger randomness that gets injected. So I totally recognize this, and the potential for using Ethernet in these was recognized. So they tried bringing in a task group to understand how we can solve this problem. We don't want CSMACD. We want a different way of using Ethernet. So time-sensitive networking is really an upgrade to the existing Ethernet standard. The way it became from 10 to 100 megabit to 1 gigabit, or the way we saw the QoS improved over time, like 10 years, 15 years ago, voice over IP was not as good as what we have today. So it would have improved over the period of time. Similarly, the time deterministic part is now being improved, and that's time-sensitive networking.
Oh, okay, that's interesting. So clearly here, from what I can hear is that the reason for bringing time-sensitive networking to the industrial Ethernet space is because of some inefficiencies that currently exist. Could you maybe come up with a list of advantages that TSN has over traditional Ethernet communication networks?
Sure. When you talk about the industrial world, when you talk about machinery and the communication within the machinery, it's like you have these sensors and actuators, and you have to cable these sensors and actuators to the controllers, where you actually have the computing power, and you then run your algorithms to take your decisions. If you simplify this problem and you really see the business case, it's really a cabling problem, right? Like you cannot have individual cables running from your controller to each and every sensor. This is going to create a problem with respect to the weight of the cables, cost of the cables, quality of service, and then a maintenance nightmare. So people started searching for alternatives to running independent cables with analog signals to each sensor, and that is how people started using Ethernet, right? Like, in fact, it's a long way. They first started using UART based protocols, and then at one point, even they were not sufficient in terms of bandwidth or ease of the connectivity, the way you connect an Ethernet cable, and the way you can change the topology and all this. So people started using Ethernet. But when it comes to using Ethernet, they had this problem of CSMACD, and they tried solving it. And each and every major company out there, they tried solving this problem in their own way. For example, companies like, for example, Siemens, they started using Profinet, coming from their Profibus background, or Beckhoff, they created EtherCAT. So all these are the base Ethernet technology with some extension on top to achieve the deterministic communication that was needed. So that's how this was created. Now, this has also essentially fragmented the industry. So what TSN is now going to do is they are fixing the original problem at the layer 2 level. And now once this is fixed, now you can have a single hardware, which will probably become the mass produced one. Like, you 5-10 years from now, you buy a laptop, the Ethernet port that comes along with it probably is fully capable of doing TSN. So then all you need is the software pieces. And I think that's the primary advantage I see. The scale of the economy of scale kicking in and bringing the price down. And you have a single hardware that can deliver the real time that you need. And then everybody can then plug in their own software on top. So that's the primary advantage. And the world will be a lot more open in the future.
Correct me if I'm wrong, but I get the sense that what you're saying is that you could have all these Fieldbus protocols running on one standardized Ethernet. Would it be possible to run all these Fieldbus protocols on a standard Ethernet using TSN? Is that correct?
It is a very, I think we have to see this in layers. We know this OSI layers in networking, right? Open system interconnection, the 7 layers. And if you look at Ethernet is a layer 2 protocol. And TSN is essentially an upgrade to the features. TSN is essentially an upgrade to the features in the layer 2. And the companies have then, in the past, with all the other Fieldbus protocols, they have built some custom extensions on the layer 2 level, and then they have built a complete software ecosystem on top, right? And when we call something as Profinet or EtherCAT, we just don't mean the layer 2 these days. So it's usually all the other layers on top. And even when you have a new standardized hardware, I'm sure all the companies are planning to continue to use their software ecosystem. They cannot just throw away years of investment and switch to something new.
Yeah.
So we will see a transition period where you will have a standard TSN hardware, and then all these existing protocols sharing this network. This is going to be the reality. But then as the market adoption starts and the need for simplification kicks in, after a point, then you will see that it is more going to be OPC UA plus TSN, and probably the other protocols will be in very small islands and more in the legacy stage.
Now, well, as you have already alluded to, time determinism is really is the foundation of TSN. So what I would like to find out from you is, what are the core elements of TSN that make it achieve this deterministic communication?
So as I had mentioned, it's a IEEE task force, right? Like they come up with the standards, and it's a bunch of IEEE standards. The first one, the most important one, is the IEEE 802.1 AS, which is the time synchronization standard, the PTP, what we call as the GPTP standard. So this is about how we can synchronize the clock, and we rely on some hardware features available to achieve time synchronization between two systems in the nanosecond boundary, right? So this is the core. You have a way of synchronizing the clocks between different systems. And so this is the first. Once you have the same clock across your network, all the compute elements in your network, then you need a way of communicating between each other. So that is where the next set of protocols come in. These are essentially upgrade to the IEEE 802.1 Q standards. Q stands for the quality of service. So we try improving the quality of service. So it is like 802.1 QAV, and QAV first was more useful in the audio video world. But once industrial guys came in and started, they realized that QAV may not be enough. And then they started working on QBV. So you can think of QBV as dedicated. It is more like time division multiplexing. So you have dedicated slots of time where you expect a certain high priority traffic on the network. So you have time synchronization, and then you have this time division multiplexing on the network where we know that, okay, I have to place my high priority frames right now. So this ensures that we are able to deterministically communicate between two nodes over a shared Ethernet medium, where you also have other traffic like an audio video or some configuration messages or some diagnostic things happening. The last one, the one I think that will help complete the solution package is your I think it's QBR, or it's about the frame preemption. Like when you have a low priority, a big frame going in, and then you have your high priority guy coming in. So you have to preempt the frame send, and you have to send the high priority guy, and then continue the larger low priority one. So this will be at the core. You have the time synchronization, you have your QBV, which is more like time division multiplexing, and then you have your frame preemption. So these three standards will be at the heart. And then you need the standards that will help configure these systems. So you will have your QCC, which talks about how these systems can be configured. So that's TSN in a oversimplified fashion.
Okay. Yeah, thank you for that. What I would also like to find out from there is what would be required then for any industrial machine or device to participate in a TSN network? Is there dedicated hardware that is required for it?
Right. There are multiple ways. One is companies like Cisco are selling TSN hardware for quite some years now. So you can buy one of these switches, and then you connect one of your device. Then this switch is going to take care of the regulating part, how the device gets access and how the TSN network is regulated. And this switch will have the capability to synchronize itself with the network and handle everything. This is the most simple use case. If you don't have, if your own device is a single ported device and it doesn't have huge real-time considerations. And when I talk about deterministic considerations, I talk about sub-millisecond response times and guarantees. If you don't have that, then this is a simple one. Like you buy a TSN switch, then you connect your device, maybe you have a basic infrastructure ready. But then when you talk about, say, existing PLC vendors and automation component vendors adopting to the standard, probably they have a two-port device, which means they have a switch inbuilt into their device now. And you have to configure this TSN switch. So this becomes a lot more complicated, and that's the reason why a lot of companies come together and work together to solve this problem.
Interesting. So you mentioned previously the OPC UA. I think let's bring that into the conversation now. So we already have protocols, for field level communication that's been there for quite some time now. What I would like to find out is, why is it important to achieve field level communication using OPC UA?
So when we speak about TSN, we talk about, TSN is nothing but a new Ethernet, right? So tomorrow, every device, when we say it has an Ethernet port, it will probably have all the basic things needed to run a TSN network. And when such a thing happens, all you need is a standardized layer of software on top to achieve all kinds of automation use cases that are visualized by Industry 4.0 world. So in this case, TSN is working like from the bottom up, right? They are trying to solve a problem from the bottom up, and OPC UA traditionally they are trying to solve a problem from the top down. So at some point, these two technologies will meet, and then you don't need anything else, and you will for the first time have a very seamless way of exchanging information from sensor to cloud using one way of information modeling and one way of information exchange. So that's why I think this is very important, and that's why this is so, it's a revolutionary approach.
Oh, okay. So maybe perhaps let's drill down a bit on the value proposition of bringing OPC UA and TSN together, because here I understand we're essentially bringing together these two standards. Can you talk to us about that?
In terms of value proposition, so what this will do is, let's take the example of Linux. Linux is quite popular in the server space, and Linux is also becoming increasingly popular in the automation industry. The main reason why this is happening is an operating system is a base technology, and when there is an open source implementation available, it is easy to build use cases on top, and it reduces the entry barrier. It reduces the fragments in the market, which means now you build a new product or a service. For example, if you build a new application that concentrates on delivering food, or when you have something like Uber where you can book a taxi, you don't have to have 100 different variants of the Uber application, and you can focus more on the business logic, wherein the underlying technology is running on a base set of standards and probably on a base set of open source software as well. So this is the primary advantage I see. When you have a base hardware which is based on standard, and all the major silicon vendors out there, they are going to implement this, then you have an OPC UA software ecosystem that sits on top. Then companies can focus on their core differentiators. Companies can then work on the core business value proposition that they want to solve, and not worry about how do I take this one bit and how do I transfer it there, and should I need this gateway, that gateway. All this unproductive thing can go away. So and whatever you build can scale globally.
Oh, okay, that's interesting. Yeah, so I think perhaps from the perspective of Industry 4.0, just to make it clear for some of the architects here in the audience, what do you see as being the major role of OPC UA over TSN, looking at it broadly from an Industry 4.0 perspective?
Right. Let me share from some of the projects we have already executed and where we have helped our customers. So, we had one of our customers, they build injection molding machines, and they also use robots from other vendors where you then draw the parts out of the machine. And you have this machine by a particular automation component vendor, and then you have this robot using a completely different setup. Now, when you have the companion specifications in both, then there is a seamless way where you can connect both of them. But this is not a challenge purely at the companion specification layer, because there is a real-time element to this particular communication between the robot and the machine. You cannot have a delay. You have to guarantee your times. And this is where OPC UA and OPC UA PubSub technology along with TSN comes in with a very important value proposition.
Okay, so I think that's quite interesting. That you've brought up OPC UA PubSub. Now, what's the major reason for having OPC UA PubSub as being the primary go-to for TSN?
Sure. So let's first understand OPC UA client server. In the client server exchanges, it's a connection-oriented protocol, and depending on the number of clients you may want to have your connect to your server, the server may have to support multiple connections simultaneously. So the cost of the server hardware goes up, right? The number of things you have to support from the server starts inflating, which limits the kind of different places it can go. For example, if you have a small sensor and there are at least 20 other devices on your network that's interested in the data from the small sensor, PubSub is a lot more efficient, because then this small device can just keep publishing the information, and all the other devices who are interested can merely consume this. So this is the primary difference between PubSub and client server exchanges. So you can take OPC UA down to the sensor level on one end. And the second thing is, publish subscribe is not connection oriented, which means you don't have losses, retransmissions, and stuff like that. And that helps us design systems with a particular level of guarantees. So I can build a system that runs at, say, 100 microseconds cycle time, and I can guarantee that an information that originates in A can reach B within 100 microseconds. How many billion times you want to run this, you will always meet this particular guarantee. So this is with respect to PubSub at a horizontal level, right? Like at a horizontal level, to a robot and a machine talking to each other, this works great. And there is also another use case, which is some of the sensor value, you may want to take it down, take it up to the cloud, and you may want to do some analytics in the cloud. Again, PubSub is a well-established concept here. For example, if you take MQTT, it's a popular protocol, and it works with this brokered PubSub model. Like you have a MQTT broker, and every device then subscribes, sends the publishers to the broker, and the broker then distributes it to all the subscribers. And OPC UA PubSub can use MQTT as a transport layer and then push data to the cloud. The key advantage here is you don't break the meta information that the OPC UA standard carries. So you have the advantage of PubSub, but then you also have the advantage of the OPC UA's metadata. So in the vertical, you can take the meta information from the sensor to cloud without breaking it. And in the horizontal, you can achieve great real-time use cases.
So you've already given us quite a long list of use cases there. Perhaps if you could maybe have some example applications of OPC UA over TSN in manufacturing facilities that you could share with us.
Yeah, so as I had already mentioned, this is great when it comes to systems where you have a multi-vendor interoperability. So you have machine coming from one manufacturer, you have a robot coming in from the other. As long as you are, you know how to tie the information between them, right? Like PubSub, who's interested in what and how they subscribe or published with each other, and a companion specification is available. This is great, right? So this interoperability is one main advantage we see. And the second main advantage we see is the PubSub protocol can be really scaled down to small devices. So in future, you will start seeing every device having OPC UA supported as a standard, and then the entire ecosystem will be extremely homogeneous. So you don't have multiple gateways sitting in between, and you don't have complex ways of handling information from different layers.
Now, to bring 5G into the conversation, what does the convergence of OPC UA over TSN and 5G mean for Industry 4.0?
Yeah, let me take a very interesting example here. Now, we all know that across the world, we are moving to electric cars, right? We are starting, so this is an automotive example, but you will see the relevance coming in. So cars are becoming electric, and mostly we are not going to cut away the charging time in the near future. So you may have to charge your car for 1 or 2 hours, and maybe you will stop owning the car, and the car may drive on its own to a charging station and charge itself. And these charging stations are going to be Industry 4.0 blocks, and the systems inside these charging stations are going to be PLCs and controllers that are going to have OPC UA and probably TSN, and probably have the ability to publish and subscribe via a 5G network. So in my mind, when I see OPC UA, TSN, or OPC UA and 5G, though it has not yet spilled over into the automotive space, I think it's a necessity, because sooner or later, a car is just another machine, and this machine is produced by one manufacturer, but then its charging station is by another guy. And when they are far away from each other, they may talk through the cloud. But when they are near to each other, there will be some amount of edge processing and edge level exchange of information. And it will be a very different world to how we do things today.
Oh yeah, absolutely. That makes a lot of sense now. So maybe to wrap up the conversation about OPC UA over TSN, are there any commercialized products for that implement OPC UA over TSN?
The answer is no. And let me explain a little bit around what is happening right now. Towards the end of 2019, the field level communications committee was formed within the OPC Foundation, and this has literally all the existing automation players in one room. And this group is now starting to publish all the specifications. And they are also having a lot of prototyping activities happening in parallel. So if you ask me whether there are existing devices in the market, no. We still have only big demonstrators and stuff, but work is happening day in and day out. The technology is a complex one. And if you are in this space, you have an aspiration to build your own devices and sell in this space, then you should be watching the work happening in these bodies closely. Maybe I should also mention about IEEE 60802 standard here, because there should be something that helps everybody come together, right? So that happened to be this IEEE 60802 standard. This standard is nothing but the TSN profile for industrial automation. So we spoke about the TSN standards, which are common across different wide industries like audio, video, broadcasting, or automotive, and the industrial. But when it comes to industrial use cases, this IEEE 60802 standard specifies the common industrial profile. And FLC was formed with this document as the basis, and a commitment to go towards the use cases listed in this document. And now today work is happening in the FLC. So if you are a device manufacturer, I will suggest you pay close attention to what is happening here and closely follow this. And we should start seeing controller to controller level integrations very soon. And maybe 3 years down the line, you will start seeing end-to-end devices.
Okay, that sounds like quite an interesting future then. We'll certainly be on the lookout for it. So, well, You are the CEO of a company called Kalycito, right? And one of the initiatives that you have at your company there is the open source crowd-funded OPC UA and TSN. Can you explain to us what it is, why it exists, who is involved, and how it works?
Sure, sure. As I mentioned, there are two different angles. One is TSN is working from bottom up, and OPC UA is coming from the top down. And PubSub is a very important piece that was needed in OPC UA for it to go from the top to the bottom. And we as a company, we believe in open source, and we believe that base technologies should be open source. And anybody across the world who wants to come into the space should have a minimal entry barrier to come in and use a technology like this. And so that's that is our motivation to come into this. Towards the end of 2017, it was quite clear that something like the FLC may happen in 1 or 2 years. And it was also quite clear for us that OPC Foundation is about to publish the PubSub specification. And we wanted to see whether we can have an open source version implemented. And we partnered with Fraunhofer IOSB in Germany. And we took the Open 62541 open source implementation of the OPC UA specification. And we made sure by the time OPC Foundation published the specifications for PubSub, we also became the world's first to publish the code, the source code, and also in a very friendly license where people can take and start using it inside their product. And this really was the start of our open source ecosystem project. And when companies like Intel and ARM, when they saw that we are doing this, and we started like this, but then we also quickly certified the stack for micro embedded device profile, and we made sure people can rely on this stack and build industrial products. And this kind of kicked off the open source ecosystem project, where we run it under the umbrella of OSADL, Open Source Automation Development Lab, who are based out of Germany. They are the guys who created. They are behind the real-time Linux patches, the RT preempt patches. And they had almost completed their job with respect to real-time Linux, and they were looking at what next. And so that's when we joined hands, Fraunhofer IOSB, Kalycito, and OSADL, and we launched this joint ecosystem project. So companies can come, tell us what they want, and they can also allocate a small budget they can share. And when many companies put money like this, then we have a pool of budget available, and we then allocate people to work on the problems that they want solved. So first, we made sure PubSub is available open source. Then we made sure the stack is certified by the OPC Foundation. And in the third phase, we implemented PubSub security. Again, I think we were the first to implement PubSub security and make it available open source. And now we are we are in the phase where we are launching the next phase of the project. So this is an ideal time people can come join in and tell us what they would like to see. And the next phase will probably, right now we are in the information gathering phase. So people can tell us what they want. And in a month's time, we will be launching the next phase of the project. So today, in the last phase, the phase 3, it was funded by companies like Intel, ARM, ABB, D&R, Siemens, and Contran were the main partners in the last phase. Hopefully, they'll continue this phase, and we'll probably have a bigger. Each time we see that the phase is becoming a little bigger. So hopefully, we are looking at a good start to the next phase in the coming month.
Okay, Christoph, thank you so much for this marvelous work that you're putting together. For the community, we'll certainly be putting the word out for this project. So now, in conclusion, can you tell us more about the solutions and services and also courses that you offer at Kalycito? And as a follow-up to that question, can you tell us more about Kalycito, the company?
Right. So Kalycito is a 15-year-old company. We started in the year 2007, and from the beginning, we have been working on industrial systems, and particularly in the real-time communication and real-time system space. And off late, we have been seeing a trend. People try to mix a Linux box and and an automation PLC into one network. So that's been an increasingly positive trend that we see. People want to have master control in the in their automation network, which takes care of their business logic, and they have a large network. So, but people don't know how to do it. People don't know how to do it in a standardized way where they use, many are new to open source, many are new to Linux, many are new to achieving real time with this kind of systems. So that's where we walk in as a consultant, help our customers onboard into this new world, and how to establish a secure connection from here to push data into a cloud and stuff like that. So we engage as a consultant, and then we also execute the project in an end-to-end fashion for our customers.
Oh, okay, that's interesting. All right, so that brings us to the end of this session. Thank you so much for taking the time to come and share your insights with the audience.
Yeah, it was a pleasure talking to you today, and I also want to thank all the Industry 4.0 TV audience, and looking forward to meet you again sometime in the future as well. Thank you.
Okay, thank you.